cathode ray oscilloscope or CRO. This is the block diagram of CRO. In this block diagram you see this is the electron gun, and this is your vertical deflection plate, this is your horizontal deflection plate, and this is your screen of the CRO. You will get actually the screen of the CRO in the form of a square or rectangle, and you can see the various waveform in this screen, which is basically phosphor screen. You see, you give input signal to the CRO. When you give input signal, it is amplified by vertical amplifier, or vertical amplification is done first. Then the signal is given to the delay line, and in the delay line the signal is fed to the vertical deflection plate. You can see it, and another signal which is coming from the vertical amplifier, it is fed through trigger circuit. You have a trigger circuit in the CRO. Then after passing through the trigger circuit, the signal go to the time base. This is the time base generator. Then the signal go to the horizontal amplifier, and after horizontal amplifier the signal is given to the horizontal deflection plate. This is the horizontal deflection plate. So in CRO you have two supply, voltage supply. One is your LV, another is your high V, HV. HV is the high voltage and LV is the low voltage supply. Basically low voltage supply is given to all the circuits, but to the CRT, that is the cathode ray tube, which we will discuss, high voltage supply is given. And this diagram is basically an analog cathode ray oscilloscope. But nowadays a digital CRO or digital cathode ray oscilloscope is also available in the market. As the electrons emitted from the cathode, this is your cathode, that is why it is called cathode ray oscilloscope. So first we will discuss about electron gun. What is electron gun? Electron gun basically consists of four parts. First part is your electron ejection, where electron comes out. Then the second part is your electron focusing. After electron comes out, then it is made to focus. So the next part is your electron focusing. And the third part is your electron acceleration. After electron focusing, the electron get accelerated. So then you have electron acceleration part, then electron deflection. After accelerating the electron, you have two types of deflection. One is through the horizontal, another through the vertical deflection plate. So in the electron gun you see this is the heater. When you hit the cathode, then electron will come out. You see how the electron is coming out. Then you have grid. Then after coming from the grid you have electron out of the electron ejection system. Then this is your focusing, or you can say pre-accelerating anode. This is your pre-accelerating anode. Then you have electron focusing anode. This is your focusing anode. Then you have accelerating anode. This is your accelerating anode. And then you have two plates. One is your vertical deflection plate. This is your vertical deflection plate. Then you have horizontal deflection plate. Then electron comes to this screen, which is made up of phosphor. So it is called phosphorus screen. So you see from the heater till this vertical deflection plate, the whole system is called electron gun. This constitute your electron gun. So first let us discuss about electron ejection. We know cathode is a nickel cylinder coated with barium oxide or strontium oxide, and it emits plenty of electrons. When these cathode is get heated, which is coated with barium oxide and strontium oxide, electron comes out. The emitting surface of cathode should be as small as possible. Theoretically, the emitting surface of cathode is basically a point. The rate of emission of electron beam depends on the magnitude of the cathode current. So how much electron beam is coming from the cathode, that we measure from the cathode current. If you connect a ammeter, then you can say how much electron current is coming, and from the measurement of current you can say how much electron is coming from this cathode. In CRO, the intensity control switch, we have a intensity control switch which controls the rate of emission of electrons. I will show you the intensity control switch in CRO, and the control of electron current is done by a variable resistor. So how you can control the flow of current or the flow of electron, and there is a variable resistor connected to the circuit which controls the flow of electron, and the brightness is increased by rotating the intensity control switch clockwise. I will show you how you can increase the intensity or brightness. More intensity of electron beam means more magnitude of cathode current or more brightness. So this is your CRO, and when you switch on CRO, I am switching on the CRO, you see electron beam coming from the cathode, it will reach the screen. You can see a bright spot on the screen. This is the beam of electron, and this is your intensity control switch. This is your intensity control switch, and the intensity control switch controls the rate of emission of electrons. You see I am adjusting or changing the brightness. I am changing the brightness, you see, by the intensity control switch by means of a variable resistor. There is a variable resistor in this intensity control switch. You can change the intensity like this. The next part of your electron gone is your electron focusing. So this is your electron focusing. After electron ejection you have electron focusing. So how you can focus the electron? The beam is focused by focusing anode. After obtaining an appropriate brightness by operating your intensity arrangement or intensity control switch, you focus the beam till the bright line is clearest. So focusing anode is to focus the beam on the screen connected to a lower voltage. Basically the focusing arrangement is connected to a lower voltage. So now you will see how there is a arrangement in the CRO to focus the electron or electron beam. You see, when you switch on, you first control the intensity, then you focus the beam. So this is your beam and this is your focus arrangement. This is the switch for the focus arrangement. You first control the intensity, then you control the focus. This is the focusing switch, and this switch is basically connected to a low voltage source. You see I am focusing the beam. The next part of your electron gone is your electron deflection. So this is your electron deflection part. So when the electron is accelerated, it passes through the deflection system. You see, this is the deflection system. This is the vertical system and this is the horizontal system. And by this system, vertical system and horizontal system, the beam can be positioned anywhere on the screen. Whether the beam, you can place the beam in x axis or you can place the beam y axis or in any place xy plane, any place in xy plane. the face of the screen can be considered as the XY plane. This face of the screen can be considered as XY plane. On the plates in each set, you see you have two sets. This is one set and this is another set. One set, that is the vertical and horizontal plane. In horizontal plane you have one set, in vertical plane also you have one set. In both the sets you have two connections from vertical and horizontal connection, horizontal plates to the ground. Suppose this is connected to the ground from the horizontal deflection plate. If this is connected to the ground, then from the vertical deflection plate, this will be also connected to the ground. Then you have another plate. This is another plate of the horizontal deflection plate and this is another plate of the vertical deflection plate. These two plates, they are connected to, are given external deflection voltage. And then these two plates are given external voltage, deflection voltage through an internal adjustable gain amplifier stage. In these two plates, you will give a amplifier to for the deflection voltage, external deflection voltage. So two plates are connected to ground and two plates are connected to the deflection voltage. And in the CRO, I will show you the terminal for the external deflection voltage. To apply the deflection voltage externally, an external terminal called the Y input or the X input is available. I will show you the X input and Y input in the CRO. A positive voltage applied to the Y input terminal, that is Vy, causes the beam to deflect vertically upward due to attractive forces, while a negative voltage applied to the Y input terminal will cause the electron beam to deflect vertically downward due to the repulsion forces. In the channel 2 input connector in my CRO, I will show you there are two connections of for the Y input. One is positive, another one is negative. The positive voltage, when you give positive voltage to the Y input terminal, the beam will be deflected vertically upward, and if you connect the Y input negative, then that beam will go downward, or it will move downward. Similarly, in CRO, you have a channel 1 input connector, and if you apply a positive voltage to the X input terminal, that is we call Vx, then it will cause the electron beam to deflect horizontally towards right, while a negative voltage applied to the beam will cause the electron beam to deflect horizontally towards left of the on the screen. You can check it in the CRO. And the amount of vertical or horizontal deflection is directly proportional to the corresponding applied voltage. And if you simultaneously apply the two voltages, that is X along X axis, Vx and Vy, what will happen? When the voltages are applied simultaneously to vertical and horizontal deflection plates, the electron beam is deflected due to the resultant of these two voltages. So the horizontal deflection X produced will be proportional to the horizontal deflection voltage Vx applied to the X input. So X will be equal to proportional to Vx. So X will be equal to Kx into Vx, where Kx is called the constant of proportionality, and the deflection produced is usually measured in centimeter. In the screen, you usually measure the deflection in centimeter or as a number of divisions on the scale. Actually, there is no symbol for, there is no centimeter sign in the screen. You have only division. So from the number of division on the scale, you measure the deflection. Then what will be Kx? You can calculate Kx like this. Kx will be equal to X divided by Vx. So X divided by Vx will be in centimeter per volt or division per volt. So Kx is called horizontal sensitivity of the oscilloscope. Similarly, in the vertical deflection Y, will be proportional to the vertical deflection voltage Vy applied to the Y input, that is Y will be proportional to Vy, or Y will be equal to Ky into Vy. So Ky is called the constant of proportionality. So Ky will be equal to V divided by Vy, and Ky can be measured in terms of centimeter per volt or division per volt. And Ky is called vertical sensitivity of the electroscope. In this way, you can calculate the horizontal sensitivity and vertical sensitivity of the electroscope. In CRO, you will find another 3 switches. One is your vertical amplifier, then time-based generator, and trigger circuit. I will show you these 3 in the CRO. Now let us discuss what is vertical amplifier in CRO. Vertical amplifier basically amplifies the input signal which is to be displayed on the screen of the CRT. And what is time-based generator? Time-based generator is used in CRO to produce the sawtooth waveform. It is in the CRO. And what is trigger circuit? In CRO, a triggering circuit is provided for synchronizing 2 types of deflections. Synchronization of CRO means controlling the frequency and phase both. As I have shown you in the block diagram, you have a time-based circuit and you have a trigger circuit, and I will explain about time-based and a trigger circuit in the experiment. So trigger circuit are used to basically synchronize 2 types of deflection. You have 2 channels, so you can give 2 types of deflection. Suppose this is one type of deflection, and this is another deflection. You see, this is another deflection, and the 2 deflection, they are not synchronized in phase. You see, the phase of this deflection is not same as the phase of this deflection. But if you synchronize these 2 waves, then the resultant wave will be like this. The resultant of this wave will be like this, and this is the synchronized wave, and you do it by means of the trigger circuit. If you use the trigger circuit, then you can synchronize this wave with this wave. That means you have to synchronize this wave in phase with this wave. You see here, the 2 waves have same phase. They are same phase. You can see it. Now we'll discuss about the application of CRO. The first application of CRO is the study of waveform. What is the nature of the wave we can study by the help of CRO? To observe the wave shape of voltage in various types of electronic circuit, the signal under study is applied to vertical input terminals. I have told you have 2 terminals. One is your vertical, another one is your horizontal. Then you first give the voltage source, what you study, to the vertical input, and you give sawtooth wave into the horizontal input terminal, that is to the horizontal deflection plate. So in the CRO, you have 2 deflections or 2 terminals. One is vertical, another horizontal. So you give the signal you study to the vertical input, and a sawtooth wave by means of a signal generator. You have to take a signal generator. A signal generator is a device where you can produce so many types of signals, sawtooth wave or sine wave, cos wave, like this. So from the signal generator you give sawtooth wave to the horizontal input. Then various controls are adjusted to get sharp and well defined signal wave from the signal wave on the screen. Then when a sinusoidal voltage is applied to the vertical deflection plate, it makes the plates alternatively positive and negative. As a result, the spot moves up and down at the same rate as the frequency of the applied voltage. So in order to move the beam from left to right at a uniform rate, a voltage that varies linearly with time should be applied to the horizontal plate, and this can be achieved by applying the sawtooth wave. So sawtooth wave is basically used to move the beam with a uniform rate. The next application is your CRO, is your measurement of voltage and current. So you have two types of measurement. One is your DC voltage measurement and current, and another one is your AC voltage measurement and current. For DC voltage measurement, I have prepared a video, that is measurement of DC voltage using CRO, and you watch it. Then how you can find out the current? If you apply Ohm's law, V equal to IR, then you can measure the current by dividing the resistance. Similarly, for AC voltage, you can follow the same principle as I have told you in the DC voltage measurement. You set the AC ground DC. You have three switches. You set the AC ground DC to AC mode. Then there is no need of matching zero level with the scale line. In DC voltage measurement, you have to match the zero level, but in AC voltage you have a signal, so there is no zero line, and you have to set the volts per division appropriately. In the CRO you have volts per division switch. You have to take appropriate division for the volts measurement. And AC voltage of the signal will be equal to number of division you have taken in the signal. Suppose you have a signal like this. I am drawing the signal like this, and from here to, let us say, here, the number of division you can calculate, and the number of division when you multiply with volts per division what you have taken in the switch, then that will give you the AC voltage of the signal. Similarly, as I have told you, the current, for the measurement of current you use Ohm's law. And for the measurement of time period and frequency of a signal, what you do, there is a time based control or sweep time per division. In the CRO you will get a switch, there you can, it is written sweep time per division, and the control at setting level of various times, like your 0.2 microsecond per division to 0.2 second per division. In my CRO, I have the time per division from 0.2 microsecond to 0.2 second. Then time base is changed by applying or simply rotating the control of the desired setting. You have to rotate the switch to find your desired sweep time per division. Let sweep time per division you have set 1 millisecond per division, and the peak of the sine wave is separated by two divisions. Suppose in the CRO screen you see the wave, the peak from one peak to another peak, the division is 2. Then what will be the time period? 1 millisecond per division, that is the sweep time, into 2, that is equal to 2 milliseconds. This will be the time period of division, because time based control controls the wave shape. And what will be the frequency? Frequency, as I have, you know, it is equal to 1 by time period. So if it is time period is 2 millisecond, then frequency will be equal to 1 divided by 2 millisecond. You can convert it into second, that is 2 into 10 to the minus 3 second. So that will be equal to, in hertz, it will be equal to 500 hertz. So in this way you can calculate or measure the time period and frequency of a signal. In the CRO you have also a magnification, MAG or magnification 10, MAG 10. If you pull it out, position of the time per division must be converted to 1 by 10, since the sweep is magnified. So in the examination, question will come like this, with a block diagram, discuss cathode ray oscilloscope, and you discuss about the electron gun. Basically, question will be asked to write about the electron gun, and also you will have question for the application of CRO, how CRO is useful to study the waveform, how CRO is useful to measure the voltage and current, and also the time period and frequency, like this. Since this video is a very long video and it is meant for the theory, so I will explain the practical of the CRO about the practical I will explain in a separate video. Thank you.